6.1 talks about antiderivatives and slope fields. And we did an activity in class about to introduce the slope fields to you, so I'm not going to address that in this lecture. This lecture I'm going to talk about indefinite integrals and how we use our antiderivatives to get those. This section starts on page 306 in your book, and you need to make sure that you have that with you for the lecture because there are some charts that I want you to look at. An indefinite integral of f with respect to x, that's what the dx means, that's what variable we're taking the integral of, is the antiderivative plus we have to take a constant. If you remember, our function little f of x is the derivative of the big F of x. This is the antiderivative of this, and it's the derivative of this. So when they go back and forth, but if you remember, when you take a derivative, the derivative of a constant is 0. So if we have this function big F of x, then we have a constant added on the end. When we take its derivative, then we're going to get rid of that constant. So what we use is we put this plus c on the end to show that we have this constant that goes with it. When you're doing indefinite integrals, this plus c is very important. You have to remember how to do that. Now, on page 307, there's a table 6.2 that gives you all kinds of integral rules and their related derivative rules that you had before. For example, the power rule, the natural log, exponentials, all those trig functions. You need to make sure you know those. Those would be a good thing to put on your spiral cards for your studying for the exam. So if you have those rules out with you, we'll go ahead and do an example of how to calculate an indefinite integral. That's the same basic principle as the definite integral. We're going to find the antiderivative. We just are not going to evaluate it at certain values. So for example, if we want the integral of negative x to the negative third plus the cube root of x minus 1 plus e to the 3x dx. So we're taking the integral with respect to x. That's what that dx means. So if you remember from our original when we did the definite integrals, if you have sums and differences, you can take the integral of the individual pieces and add it up. So we're doing antiderivatives of the individual pieces and adding those up. So this first piece here is going to use the power rule. So the power rule tells us that we raise the exponent by 1. So we have negative x to the negative second, we raise it by 1, divided by, and then whatever this number is here. So that's our antiderivative for this part. Now this here we also use the power rule on, because if you recall, the cube root of x is the same thing as x to the 1/3. So we are going to use our power rule on that one as well. We raise it by 1 and divide by that raised by 1 value. And then again here we've got a constant, but we can also think of that as our power rule. If it's n equals 0, then we have x to the 0 power is 1. So we raise it by 1 and divide. So we're x to the first divided by 1. And then this last part here is an exponential. And if you look at your exponential rule, that's the second one on your table 6.2 there, you just rewrite it and then divide by the number in front of the x there. And then we always put our plus c on the end. Now of course you can simplify this all down. The negative divided by negative makes that go away, and a negative exponent means we put that on the bottom. Divided by 4/3 is the same thing as multiplying times 3/4. So you can clean it up a little bit. But in the end, this is the integral of this function here. So here this equals that. So we just take the antiderivative of each individual piece and put our plus c on the end. So I'm going to give you another one. And I want you to pause the video and try this one on your own, and then we'll go over it. Alright, so use those trig rules there and solve this one out. So pause the video and see if you can get this one on your own. Alright, hopefully you paused it and you've got it. If you look at this, we've got the sine of x. The antiderivative of sine is negative cosine. So the constant just stays out front. So we have negative 3 cosine x. And then here the antiderivative of negative sine is cosine. And since we have this number multiplied inside there, we have to divide by that, because remember when we took the derivative, you multiply by it, so we want to make it end up being just 1. And then we always put our plus c on the end. So hopefully you've got this. And that's finding the antiderivative. A differential equation, if you recall, a differential equation is an equation containing a derivative. Just like in algebra, when you want to solve an equation, you use inverse operations, and to undo a derivative, we take an integral. Make sure you have that plus c on the end because you've got to deal with that constant. When you solve a differential equation, that means you find a unique equation that satisfies some initial equation. So for example, if we have a differential equation, we've looked at these a little bit before, where we say dy dx equals sine x, and they give us this initial value. This initial value here is so that we can find the c, when we find the plus c. And what we do is something called separation of variables for us to be able to solve this. So we separate this out, so we have dy equals the sine of x times dx. Now we can undo the taking the derivative by taking the integral. When you take the integral of dy, you just get y. Now yes, you should have a plus c there, but we're going to take care of the plus c with 1 on the end of this here. Okay, so the integral of sine is negative cosine. So we have our y plus c, but we move that over here and put it all together with the plus c that we have here. So we have negative cosine x plus c. Now, we know that this is our equation, but we need to know what this c is for this specific instance. So we take our x equals 0, and that means y is 2. So the cosine of 0 is 1. So we've got 2 equals negative 1 plus c. So c equals 3. So that means that our answer, our equation that goes with this particular situation, is y equals negative cosine x plus 3. So when you have a differential equation, you use your separation of variables and then take the integral of both sides, so you get your antiderivatives. Make sure you have that plus c there. Then you use your initial value so that you can solve for c, and that'll give you your equation. Now, what happens if we're given a second derivative? Remember, this means it's the second derivative, 2 minus 6x. And then we're given an initial value for the function and for the first derivative. Well, the first thing we need to do is we separate our variables. And then when we take the integral, remember the integral undoes the derivative, but it only undoes one of them. So we end up with dy equals 2x minus 3x squared, because we have to divide by 2, and then our plus c, and that's dy, or times dx, because we just took the first derivative. We undid one derivative. So we've got our first derivative is equal to 2x minus 3x squared plus c. Well, we have this initial value here to figure out, excuse me, what the c is for this derivative. So our derivative value is 4 when x equals 0. So that means our c is 4. So now we have dy dx is 2x minus 3x squared plus 4. So now we can step it again. Do our separation of variables. Take the integral of both sides. Now we're undoing the first derivative. So that means we get to our function. And we end up with x squared minus x cubed plus 4x and plus c. Always have that plus c. Then after we do the plus c, we can look at this to find out what that c is. So our y value is 1 when our x value is 0. So that means c equals 1. So our original function is y equals x squared minus x cubed plus 4x plus 1. So when you have the second derivative, you do the same thing, but you're going to have to go through finding the first derivative first, and then once you found the first derivative, then you can go through and find the original function. Now, that's pretty much section 6.1. Make sure you've read through this section, especially that chart on page 307, and then at the bottom of page 308, there's a few more properties for you to look at, and you can see exactly how all those work and read through those examples. There's some application examples that I want you to look at, and then we'll go over some more in class and answer any questions you have.